In this section, we're going to be talking about two theorems that are very important in calculus. We call them existence theorems because they literally just tell us that something exists, okay? Before we go into what these theorems are, I have a little challenge for you, okay? So I'm going to challenge you to draw something in the most creative way that you can think of, okay? I want you to draw a function, and remember, functions pass the vertical line test, so you can't make it not pass the vertical line test. The function has to be continuous on -4 to +4, which means you can draw it without picking up your pencil, right? It also has to be differentiable, which basically means you can't have a sharp corner, right? Can't have a V-shaped graph, no jumps or anything like that. And then the final thing I want you to do is to make sure the point for -4 and the point for +4 are at the same height. Okay, so f of -4, the y value there, has to be the same height as f of 4. All right, I'm going to give you a minute to draw the most creative graph you can think of, and I'm going to ask for some volunteers to write them up on the board here. Nice job there. All right, I saw some good ones here, but I'm gonna leave it with these three. Okay. So looks like we got a couple graphs here. I actually saw James write another one, but I'm not gonna ask him to write this twice. But James actually wrote a cool one that I thought was interesting. He made the 2 points be at 0, so they were at the same height, but the line was just a straight line. So that one's an also interesting one to think about too. All right, let's go through what I'm actually looking for on these graphs. Let's go through these graphs and see if there's a place, okay? Let's look for a place where the derivative is 0. Okay, so where our function is either constant or turning around. In my first graph, where's my derivative 0? At the bottom, right? It looks like the derivative is like 0, I don't know, around here, right? So that looks like a spot where my function, the derivative is 0, okay? Now, Jude did a good job on the second graph. That was a pretty interesting one. And it looks like there's not just one place where the derivative equals 0, but multiple places, right? So there's one here, 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 over here, here, and here. There we go, right? So very nice job. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 places where our derivative equals 0. So nice job there. Okay, didn't realize someone already wrote that one on the board, but Cole did another one where the derivative equaled 0 once at the bottom. Okay, how many places does the derivative equal 0 on my last example? Is the derivative equal to 0 here?
It's basically infinite.
Infinite, right? The derivative is 0 here because a constant function, if you drew a tangent line, the slope of that tangent line would be 0. Literally, the slope of this line is 0, right? Slope equals 0. And as Jude said, at any point, it seems like the derivative is going to be 0. This is an example of a constant function. Remember, constant functions have a 0 derivative, okay? And this one actually has like a million places or an infinite amount of places where the derivative is constant, okay? All right, so I told you to draw a function that's continuous, differentiable, and the two endpoints are at the same height. Do you think there's a way to draw a graph where the derivative doesn't equal 0? With these constraints.
Just do linear.
If it was linear, let's see what would happen. The endpoints wouldn't match, right? So that wouldn't work. Any way we can do this without the derivative being 0? I don't hear anything, so I guess the answer is no, right? Okay, that's actually right. Okay, there's no way you could draw a graph that meets these specific criteria and the derivative not being 0 somewhere here, okay? And what this is actually saying is, well, this is literally what Rolle's theorem says, okay? So a very important theorem of calculus is called Rolle's theorem, okay? And we have the 3 hypotheses. First, we have f being a function. The function has to be continuous on the interval a, b, so the closed interval, like -4 to 4, basically. It has to be differentiable on the open interval a to b, so -4 to 4. Talking about the closed versus open interval, I wouldn't really worry about closed versus open here. I'm not going to trick you with these, but just think continuous, differentiable. And the beginning point has to be the same height as the ending point, okay? So the 2 endpoints have to have the same height. If these 3 things are true, then there is a number c, okay? So there's an x value in this interval between -4 and 4 where the derivative equals 0. Okay, so there's some number in between -4 and 4 where the derivative has to equal 0. Does this mean there's only one number? No, right? Jude's graph had 17 numbers where the derivative equaled 0. And then the final graph had a million or an infinite amount of places where the derivative equals 0, okay? So what this is saying is there has to be some number. It could be a million, billion numbers, could be an infinite amount of numbers where the derivative equals 0 if these 3 things are satisfied. Okay. Let's do a few examples on maybe something a test might ask, and we'll continue on here. Okay, so any type of Rolle's theorem question, first is going to ask you if a function satisfies the 3 hypotheses of Rolle's theorem. So continuous, differentiable, endpoints have to be at the same height, okay? If that's true, you're going to be asked to find all the numbers c, all the x values that satisfy the conclusion. Where does the derivative equal 0? Okay, so let's do this one. We have sine of x on 0 pi, okay? So using our theorem, a is 0, b is pi. Okay, let's go through the 3 things here. Is sine of x continuous on 0 to pi?
Yes.
Yeah, right. Sine of x is always continuous. Doesn't matter what the interval is. So sine of x is continuous on the closed interval 0 to pi. Okay, honestly, on a tester quiz, I'm not gonna care if you forget if it's a closed interval or an open interval. Doesn't matter too much to me as long as when you go into a higher level math class, it'll be a little bit more important. Okay, next we have to think about if our original function is differentiable. Is sine of x differentiable on my interval? Yeah, right. The derivative of sine is cosine. You can take the derivative anywhere. So sine of x is differentiable on the open interval 0 to pi. Okay, now don't worry too much about closed versus open here. Just bear with me here. Okay, now what's the 3rd criteria asking us to do? How should I check to see if f of a equals f of b? Did you say? Oh, I thought you said limit. I was like, I don't know where the limit's coming from, but yeah, plugging them in, right? So the next thing we're going to do is literally plug in our a value 0 and plug in our b value pi. What are we looking to happen here? So what do we want to happen? Yeah, we want the numbers to equal when we do both of these. Let's see what happens. What's the sign of 0? Not quite. It's 0, right? If you drew the graph of sine, it would look like this: 0 to 2 pi. Let's see, we got pi in the middle. Sine starts from 0, goes down and up, right? So sine of 0 is definitely 0. What's the sign of pi? Look at the graph I just drew. 0, right? Sine of pi is 0. Okay. Since these 2 match, we do satisfy the criteria. Okay. So yes. Okay. We haven't finished the question yet because it says if the answer is yes, we do have to find all the numbers C that satisfy the conclusion, which means we have to find all the X values where the derivative zero, right? So guess we have to find the derivative first. What's the derivative of sine of X?
Cosine of X.
Okay, sine of X, good. Okay, we want to find all the places where cosine of X equals zero. Okay. How do I find this?
Make X equals 0.
Yeah, X equals 0. I guess that would work. But we're also looking at the interval 0 to pi, by the way, in the question. So let's not think about anything else. You can either draw the graph of cosine and see what happens, right? We start at 1, we go to 2 pi, and at pi, we're down here. Oops. Oh my goodness. Right? Or you can take the arc cosine of both sides, right? So we could do arc cosine of both sides of the equation. Right? So X is equal to the arc cosine of 0. Now, honestly, that's a little bit of a reach thinking about what that might be. Your calculator could figure it out. But what cosine value gives me 0? Or what X value gives me the cosine of 0? Not quite. It's going to be an angle, right?
Pi over 2.
Pi over 2, right? Look at the graph of cosine. Okay. When X is pi over 2, the graph has a height of 0, right? So that's how we know that cosine of pi over 2 equals 0. Since that's true, X is pi over 2. Okay, now pi over 2 is between the two numbers that I'm looking for, okay, between 0 and pi. So that is my C value that satisfies the conclusion of Rolle's theorem. Okay. Any questions on part A? All right, let's go over to part B here. I promise I'll let you do some of these on your own, but I do want to talk a little bit about this, okay? We have to see if we satisfy the conclusions of Rolle's theorem, right? So let's go ahead and do that. First of all, we have to look and see if our function is continuous, right? So if our original function x minus 2, is this function continuous on -2 to 2?
No.
Can I draw it without picking up my pencil?
Sorry, yeah.
Yeah, right. It's definitely a continuous function. If I drew it, I would not pick up my pencil and just draw it. So it definitely is continuous on -2 to 2. So it definitely satisfies that. Is my function differentiable on -2 to 2?
It's got one of those sharp corners.
Yeah, right. If I drew this function, it would be the absolute value function, which is a v, and then moving it down twice, right? So it would kind of look like this. There's a sharp corner at x equals 0, right? So sharp corner. We know that whenever there's a sharp corner, can't take the derivative, right? So because of this, my original function is not differentiable on my open interval -2 to 2. Okay, so not differentiable. Does Rolle's theorem apply here now?
No.
No, right? Because we don't satisfy the criteria to use Rolle's theorem, we can't use Rolle's theorem. Okay, so can't use Rolle's theorem. Okay, should I even go and see if the endpoints match? No, right? Don't need to do that. Already figured out we can't do it. And because of this, we're not even going to answer the question and find the C values because, well, Rolle's theorem doesn't guarantee one. All right. If you flip to the back, I have another example for you. I would like you to check to see if Rolle's theorem applies here. We have a polynomial. And if so, I would like you to find the X values that match the conclusion of Rolle's theorem. All right, let's come up to the front here. So this one, instead of like sine or cosine or something, this one was a polynomial. And we're looking at the interval -1 to 3. Okay, so first of all, we have to see if it actually satisfies the properties of Rolle's theorem. So Jude did this one, right? Do you want to take us through the different properties? Oh, Jude. Jude.
Yes.
Oh, do you want to take us through the properties? Sorry.
Yeah, so we know that because it's a polynomial, it can be easily continuous on -1 to 3.
Mhm.
And because it's also being a polynomial, it is differentiable on -3 to 3.
Mhm.
Sorry, -1. Sorry.
Yeah, you're good.
Yeah.
We got it.
And now we're putting it to -1, which will give us 21 at the end.
Mhm.
And with h of 3, it also gets thrown in, so h of -1 equals h of -2. Yeah, because they're not the same, we know we can find.
Perfect, right? So satisfies the three conditions. Now, no matter what the question is for Rolle's theorem, you have to write the three properties. So I know some of you went ahead and found the derivative and found the number that satisfies it, but when I'm doing a Rolle's theorem question, I'm looking for you to say that h is continuous, h is differentiable, and for you to plug in the endpoints. Okay, so that's the first thing you need to do. All right, next, Blake did a great job of writing out what number actually satisfies the conclusion of Rolle's theorem. Do you want to take us through how you got that one?
Yeah, so you find the derivative of h of x and you get 4x minus 4. And you set that equal to 0. You find where the derivative equals 0, and then you solve for it.
Perfect. So looks like 1 is the only place where the derivative 0, so we're good. All right. Any questions on Rolle's theorem? Right. Now you might be asking why Rolle's theorem is really important. And basically the reason Rolle's theorem is important is because it's very essential in proving this thing called the mean value theorem. Okay, so the reason Rolle's theorem is even important is because it plays a part in proving this other theorem, which is kind of like an expanded version of what Rolle's theorem says. So the mean value theorem, I'm sure you might have heard this a lot in calculus or when people talked about calculus before. But let's just see what is happening here, okay? The mean value says that if f is a function, so it passes the vertical line test, and it satisfies two of the things. First of all, f is continuous on the closed interval, f is differentiable on the open interval, and we don't really care about the heights of the endpoints. So it's basically Rolle's theorem's condition without the last one, okay? If these two things are true, we know that there's a number, c, between our two endpoints where the derivative is equal to this formula here, okay? Now you might be asking, what in the world is this doing and how does this help us, right? Okay, we know that f prime of c is a slope, and since it's a derivative, it's actually the slope of a tangent line, right? So this is the slope of the tangent line. Okay. Now, I'm gonna try to test you here. When I first introduced derivatives, I gave you this formula. Does anyone remember what this formula was of? Not the midpoint. It's definitely a slope of something.
This one like x minus delta x or something.
It might have included that. Maybe this was a different, I think I'm using different terms here.
It's like the limit has delta x approach 0.
It's in that same area, right? So we said, okay, the way that we got the derivative was the limit as delta x approached 0 of actually this equation here, okay? Now this equation was the slope of the secant line. And the reason the limit, we did the limit as delta x went to 0 was because as the slope of the secant line, as we got, as the endpoints kind of narrowed in close to the number that we wanted to find, we got closer and closer and closer to the slope of the tangent line, okay? Now, let's kind of picture this a little bit better because I feel like when we draw a picture, everything makes sense a little bit more, okay? So let's just say A and B are here in the picture, okay? And let's just say let's figure out what f of a and f of b are, right? So looks like f of a is the height at x equals a. Looks like f of b is the height of our function at x equals b, right? Okay, and the slope of the line, well, first we have to draw the line between these two, right? So let me connect these two endpoints the best I can. Okay, what I just drew here is a secant line, right? I connected the 2 points. This is a secant line. Okay, what the mean value theorem is telling us is that between A and B, there is a point where the slope of the tangent line actually does equal the slope of the secant line. And it's kind of hard to actually figure out exactly what point it is, but it seems like the point might be around, I don't know, like here. Okay, so if we drew the tangent line here, let me see if I can do good drawing this. Right here in blue is my tangent line. Okay, do you kind of see that at that specific point, the tangent line is parallel to the secant line? Okay, so at this x value, let's see what x value this is. Over here, I'm going to call it c. This value of x gives us a point where the tangent line's slope is equal to the secant line slope. Okay, so that's what the mean value theorem is telling us about. There exists a value c where the slope of the tangent is equal to the slope of the secant line. Okay, any questions on the mean value theorem? All right, let's go to the next page, and I'm going to show you what else can happen with the mean value theorem. In this example, I gave you 1 point where this happens. There actually can be multiple points, okay, just like Rolle's theorem. Let's take a look at this one here. So this graph has a lot of stuff going on here. All right, so I'm going to make, I didn't write what a and b equaled here, but I'm going to make a really close to the x-axis here and b kind of far away on the x-axis as well. Okay, meaning f of a would be, well, the height at x equals a. I know that f of b would be the height of the function when x is b. Okay, well, let's draw the secant line connecting the 2 dots. Okay, so, oh gosh, I might need my line drawer here. Okay, so in orange, I just drew my secant line. And let's just find a point where the slope of the secant line is the slope of the tangent line. Okay, now I can think of one place where this happens. I would say about here. Okay, if I drew my tangent line to this, to the graph at this point, it would look kind of like this. And I know it's not perfect, but you can kind of see that this slope does lie parallel to the secant line. Okay, is this the only point where this happens? No, right? Let me do another one about here, right? So over here, it looks like the slope of the tangent line matches up with the slope of the secant line. And there's actually a third point where this happens. I would say here, right? If I drew my tangent line here, my tangent line is parallel to the secant line. Okay, so there's actually one value, C1, another value, C2, and a third value, C3, where the mean value theorem actually runs true. Okay, so it doesn't have to be just 1 point, can be multiple points where this happens. Okay, let's do an actual example here. Okay, so let me show you what a mean value theorem question might look like, and then what you do to actually go about this. Okay, so example 2 says verify that the function satisfies the hypotheses of the mean value theorem on the given interval. And then we're going to find all the numbers C that actually satisfy the conclusion of it. So we're going to find all the numbers where the secant line lies parallel to the tangent line. Okay, this example, we have 2x squared minus 3x plus 1 on 0, 2. Remember, there's 2 things that we have to talk about. First of all, is our function continuous on 0, 2? Yeah, right. All polynomials are continuous. You can draw them without picking up your pencil. Okay, so 2x squared minus 3x plus 1 is continuous on 0, 2. Okay. Is our function differentiable on 0, 2? Yeah, right. Polynomials are differentiable. We all know that. Minus 3x plus 1 is differentiable on 0, 2. Okay, now if you get confused between open versus closed intervals, I'm not gonna be too hard on you for that. Don't worry about it until you get into a higher level math. Okay, so does the mean value theorem apply here? Yes, right? MVT, or the mean value theorem, applies. Okay, because it applies, well, let's find that value of C that happens. Okay. Well, the mean value theorem says there is a value C where f prime of C equals f of B minus f of A over B minus A, right? Well, since f prime is in here, let's find the derivative first. What's our derivative of the function?
4x minus 3.
4x minus 3. Perfect. Okay, so let's start plugging things in. In this case, we want to find C. Now, I don't really care if you use the C or X, but it looks like f prime is 4x minus 3, which is the left-hand side of my equation. Okay, so instead of writing f prime of C, I write 4x minus 3. Okay, next we want to find f of B minus f of A. What is f of B? F of 2, right? B here, let me write this in a different color. B is 2, A is 0. So maybe I'll just write f of 2 minus f of 0 over B minus A is 2 minus 0. Okay. All right, well, let's figure out what these are. 4x minus 3 equals, what is f of 2? Kira? Oh, yeah. Oh, f of A. Oh, I didn't actually plug in 1 yet. So I just wrote f of 0 instead of f of 1, just because A is 0 there. Yeah. Good question, though. All right. Basically, what we're doing is plugging in the numbers into the equation, right? So to find f of 2, I would do 2 times 2 squared minus 3 times 2 plus 1. Okay. And then, you know what? This is getting kind of messy, isn't it? Why don't I go on the side and actually figure out what these values are? Let's do f of 2, and then we'll do f of 0 on the side so it doesn't get all messy. F of 2 is 2 times 2 squared minus 3 times 2 plus 1. Okay. Did everyone get 3? Good. Okay, now you can do this in your calculator, but to save time, just 3. Let's do f of 0. That would be 2 times 0 squared minus 3 times 0 plus 1. Did everyone get 1? Good. All right. So plugging things in here, it looks like we have f of 2, which is 3. Okay. Oh no. Gotta screw in my pen a little bit. There we go. Which is 3. I'm subtracting off f of 0, which is 1. And I'm putting this over 2 minus 0, which is 2. Okay. Well, this is getting easy to solve, right? 4x minus 3. Looks like 3 minus 1 is 2 over 2. Okay. So this becomes 4x minus 3 equals 1. Solving for x, we can add 3 on both sides to get 4x equals 4, and then divide by 4 to get x equals 1. So it looks like 1 is the number between 0 and 2, where my slope of the secant line equals the slope of the tangent. Okay. Any question on example number 2? It's a little bit messy, but honestly, not too hard. Just have to keep everything kind of tabulated a little bit. But just to give you a little bit more practice, why don't you give part B a try. A little bit harder of a function, but I think you can do it. I'm seeing some good answers, but I do want to get through this example by the end of class. So I'm actually going to go over this one at the front of class now, if that's it, right? All right, so oh, that's a cool noise. Okay, let's go to part B. First, we have to see if mean value theorem actually applies here. Okay, let's see. Is the natural log function, is that a continuous function? Yeah, you can. I saw the thumbs up. You can draw without picking up your pencil. This one is actually kind of weird because we also have to think about if it's continuous between the two values. Now, the graph of natural log, if you might remember, looks like this, right? So it looks like the natural log function doesn't even exist for 0 or lower. But between 1 and 4, the natural log function exists and it's continuous. So that's good. Okay, so the natural log of x is continuous on 1, 4. Is the natural log differentiable? Yeah, right. You can take the derivative of natural log for any value that it's defined on. Okay. Next, I asked you already, but the derivative of k is 1 over x. Cool. All right, let's try to figure out what we can do next. Since these two things are true, the answer is yes, we can use the mean value theorem, so we can continue on. So let's just figure out what we can do here. We know that the mean value theorem says that the derivative of x, or the derivative of c, is k of b minus k of a over b minus a. That's just what the mean value theorem says. Well, I already know what the derivative is. What is k of b? K of 4, right? And what is k of 4? Natural log of 4. Good. A mistake I see a lot of students make is plugging in 4 into the derivative instead of the actual function. Remember here, we are plugging in 4 into the actual function, okay? So if you want to make a note to just help you remember, plug into OG function here. Okay. Next, we're going to subtract off k of a, which if k of b is ln 4, then k of a is ln of 1. Okay, and we're putting this all over 4 minus 1. Okay, let's see what we can do here. ln of 4 is kind of just by itself here, right? I can't really simplify that anymore. It would probably be fraction or decimal. What's the natural log of 1? 0, right? That's one of the ones you have to know. And 4 minus 1 is 3. Okay, so we have that 1 over x is the natural log of 4 over 3. Okay, now x is in the denominator. How can we make this x in the numerator?
Both sides by x.
Good, multiply both sides by x and then like divide over. Or we can just flip everything around, right? Because, well, if 1 over x is this, then x over 1 is 3 over the natural log of 4. So that's a little trick we can do. If you want to multiply by x and then multiply by the 3, that's also fine. But this is a little bit faster. Okay, so x is equal to 3 over the natural log of 4. Okay, so we found our value x, where the slope of the tangent line equals the slope of the secant line. How do I know that 3 over the natural log of 4 is between 1 and 4? Yeah, just plug in your calculator, right? Now, normally we leave things like this. If you were to type your answer into WebAssign, you would definitely want to leave it like that. But just to check to see if it's in the interval, and that's the number that we're looking for, this ends up being 2.16, I think. Okay, so that wouldn't, WebAssign probably would not take this, but this is the x value that satisfies the conclusion of the mean value theorem. All right. Any questions on part B? All right, that's all I have for you today. Next class, we'll talk about actually being able to sketch a graph based on the derivative values. And I will see you tomorrow.